Hey everyone, welcome back. So do you ever have this moment when you're learning data science or something else where you learn a concept and it just kind of blows your mind? And the reason it blows your mind is because there's some other concept, probably very early on in your journey, which you realize is just a special case of this new concept that you learn. That's exactly what happened to me when I learned about the multinomial distribution. I realized that at least two distributions that we hold near and dear and we probably learned very early on in our data science careers can be viewed as special cases of the multinomial distribution. And when you do view them as special cases, you see the entire picture. You realize that you were just so zoomed in looking at a specific thing, but you realize zooming out that that thing was just a part of a bigger whole. So enough cryptic talk, let's get into it. The setup for today is that you visit the world's biggest fish convention, Fishcon. So you go to Fishcon 2023, and you see people who are fans of one of two fish. There's salmon fans and there's tuna fans. So these people are decked out in merchandise, they have their swag, they have shirts and shoes and hats, fully representing their team. So in this setup, there's two categories, salmon fans and tuna fans. And you're gonna go up and ask one person, are you a salmon fan? And they're going to give you back an answer, and we can just turn that into a number 1 if they are a salmon fan, and 0 if they're not a salmon fan, so they're a tuna fan by default. What distribution do we use to model this 0 and 1? Well, this is probably the first distribution you ever learn in your statistics course. And this is called a Bernoulli distribution. So if you just need a quick refresher here, a Bernoulli distribution models exactly this setup. So you might have learned it in the context of heads and tails for a coin. So there's some underlying probability that the coin will come up heads. Just the same way, in our setup, there's an underlying probability, P sub s, that the person likes salmon. And that's the only parameter for the Bernoulli distribution. Given that parameter, you fully have parameterized a Bernoulli distribution. So for two categories, heads and tails, or salmon and tuna, you're going to ask one person, or you're going to flip one coin, and you're going to record the outcome, which is dependent on this underlying true probability for the Bernoulli distribution. So nothing too new going on here. Let's move it one step further. So we had two things going on here. We had two categories and we were asking one person. Let's make one of these more general. Let's make the second one more general. We're still going to have two categories here. So it's still either a salmon fan or a tuna fan. But instead of asking one person whether they like salmon, we're going to ask many people whether they like salmon and add up all of the yeses to get the number of total people in that group that like salmon. And if we think about this for a second, this is actually the same setup as another distribution that we learned probably right after the Bernoulli distribution, which is the binomial distribution. Binomial distribution. The binomial distribution, again in the heads and tails case, is exactly saying, given some underlying probability of success, of coming up heads, or in our case, of someone saying they like salmon, and given n people that I'm going to ask, so you could ask 5 people or 10 people or 20 people if they like salmon, and we're going to count the number of people that like salmon or count the number of heads that we see. That's exactly a binomial distribution. So binomial distribution is fully parameterized by that P sub s, which we also needed to parameterize the Bernoulli distribution, but now we also have an n, a general number of people that we're going to ask, and we're going to count up all of the people who tell us they like salmon. And now you've probably seen this already, but there is a link already between the Bernoulli distribution and the binomial distribution if you just fix this n equals 1. If you fix n equals 1, then this becomes I have two categories and I'm going to ask one person, which is exactly the setup we're in here. And what does it mean to add up the number of people who like salmon if you just ask one person? Well, that's either going to be 1 or 0. 0 if that person doesn't like it, and 1 if that person does like it. So you see, we are exactly identically back in the situation of the Bernoulli distribution. So the Bernoulli distribution is a special case already of the binomial distribution. Now let's move to a distribution that you may have not seen before. And we're going to do that by relaxing a different one of these two criteria. So we went from two categories asking one person. We relaxed the second one to get to the binomial distribution where we had two categories asking many people. What if we keep the second one? We're still going to ask one person, but we relax the first one. Instead of two categories, there's many categories. So real life case, you can imagine Fishcon goes on for more years, and you have salmon fans and tuna fans, but a new faction has emerged, the cod fans. So now you have people who like salmon, who like tuna, and who like cod. So you have the cod fans. I'm going to draw a really quick fish here. So you have all these cod fans as well. And we're going to ask one person which category they fall into. Are you a salmon fan, a cod fan, or a tuna fan? And the answer they give us, whether it's salmon, cod, or tuna, is modeled via what's called a categorical distribution. So a categorical distribution is fully parameterized by k probabilities, given that there's k classes. So now we have 3 classes, so we need 3 probabilities in order to fully parameterize the categorical distribution. We need the probability that someone would be a salmon fan. We need the probability that someone would be a tuna fan. And we need the probability someone would be a cod fan, with the added restriction that the sum of these probabilities need to be equal to 1. Because we assume that these are all the categories that exist in the world, and they're all disjoint. You have to be in one of the categories, and therefore if you add all of these up, then you should get that equals 1. So technically speaking, you need k-1 probabilities to parameterize a categorical distribution, because once you pin down k-1 of them, the last one has to be whatever it needs to be in order to make the sum equal to 1. But in general, we can say that there's 3 categories, and we have 3 probabilities we need in order to fully define a categorical distribution. And the probability function for a categorical distribution is very straightforward. It's just taken straight from these probabilities themselves. Given you ask that one person what category they're in, what's the probability that the answer they give you, so this big X here is the answer they give you, is equal to I being either, well, 1, 2, or 3, cod, salmon, or tuna? Well, you just take the probability of that I from this list. So if you ask, what's the probability that the answer comes back cod? Well, it's just the probability of people that are cod fans in the first place. So not too much crazy stuff going on there. Now again, the Bernoulli distribution can be viewed as a special case of the categorical distribution, where when you have many categories, so if the k is the number of categories, you just set k equals 2. So if you had k equals 2, then you don't have this cod category, and you're exactly back in this case of salmon versus tuna. You just need 2 probabilities, or very technically speaking, just the 1 probability, because the probability of tuna would just be 1 minus that. And the probability that someone would give you an answer, would tell you that they like salmon, is exactly just this probability of salmon. So the Bernoulli distribution is already a special case. So I can draw that via some arrows. The Bernoulli distribution is already a special case of the binomial distribution, and it's also a special case of the categorical distribution. Now you may or may not have seen where we're going next. Because we had these 2 criteria, and we've relaxed one at a time, the multinomial distribution, all it's doing, folks, is just saying, what if we just relax both at the same time? So we had 2 categories asking one person. What if we have many categories and we're asking many people? That is exactly, folks, what gets you to the multinomial distribution. So many categories ask many people is the multinomial distribution. So concretely, it's parameterized by all these parameters. So the number of probabilities as the number of categories you have. So let's say we have 3 fish again. So probability you like salmon, probability you like tuna, probability you like cod. And of course, those probabilities need to add up to 1. And we also have n, just as we did in the binomial distribution, for the number of people you're going to ask. So the thing that's being modeled by the multinomial distribution is the counts of people who like each of the categories. So that's a lot to talk about, but you can fully capture it in this probability here. So in the multinomial distribution, you're trying to find out what's the probability that the number of people who like the ith category in my sample of n people is equal to x sub 1. And the probability the number of people who like the second category in my sample of n people is equal to x sub 2. So let me speak concretely for a second. In this FishCon example, we are modeling the probability that there are XS people who like salmon, XT people who like tuna, and XC people who like cod in my sample of n people from the total population. And as you might expect, there's some restrictions here. So as we said, these probabilities here must add up to 1 for the same reason they had to add up to 1 in the categorical distribution we just talked about. And also these x sub I, so x1, x2, all the way to xk, which is the number of categories you have, in our case 3. The sum of those counts need to add up to n. Because you sample n people, and each of those n people fall into one, exactly one, and only one of these k categories. Therefore, when you add up the number of people in category 1, category 2, category k, that needs to be equal to the number of people you sampled in the first place, which is n. So we have these 2 restrictions. Sum of probabilities is 1, sum of the number of people in each category is equal to the total number of people. Now, how do we calculate the probability mass function, how do we actually get a formula for this? We're going to need to do some cool combinatorics. So you may or may not have studied combinatorics, but I'm going to try to keep this pretty casual and kind of explain what's going on behind the math in this very ugly looking formula down here. The question we're trying to answer is, well, let's keep it concrete. Let's say there's 6 people that we sample, and let's say we're trying to figure out what's the probability that 1 person likes salmon, 2 of those people like tuna, and 3 of those people like cod. Let's say that's the probability that we're trying to estimate. So starting with the first of these questions, what's the probability that 1 of these people likes salmon? Well, there's 6 of them, so the first thing we're going to pin down is, well, which one could it be? So this bracket notation thing you might have seen or might not have seen before, we read it as n choose x1, which is saying, given n things, what are the number of ways you can choose x1 distinct things from that list? So in this case, concretely, we're saying n choose 1. So let me write it up here. Not much space on this page. N choose 1 would be saying, given I have 6 things, n is equal to 6, what are the distinct number of ways I can choose 1 thing from that set of n people? N choose 2 would be the number of ways I can choose 2 distinct but crucially unordered set of items from that overall set of 6 things. So in answering this question, we're generally saying, first, choose x1 things from that n to be in the first category. So that's n choose x1. Then we multiply that by the probability that those things are actually in that first category. And what's the probability that something actually is in the first category? Well, that's going to be p1. And since there's x1 things, and they're all independent of each other, it's going to be p1 times p1 times p1 times p1. How many of those p1s are there going to be? Well, there's going to be exactly x1 of them, because that's the number of things that we're considering are going to be in that first category. So this whole thing you can think of as a single unit, as a single action. The first thing is counting the total number of ways for which items can be in that first category. And the second term, this p to the power of x term, is actually calculating the probability that those things would be in that category. And we just continue on that way. So you can see this as a very parallel term. After we pick and assign those x1 things to be in the first category, how many things do we have left in our sample of n? Well, it's going to be n minus x1. And now we say of those remaining n minus x1 items, we need to choose x2 of them to be in the second category. So that's exactly what we do here. Now, what's the probability that those things are actually in the second category? Well, there's x2 of them, and the independent probability of any of them being in the second category is p2. So we get this identical term to this one here, where we have p to the power of x2. And we just do dot, 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 and the final one is saying after we consider x1 all the way to xk minus 1, so the second to last category, we have n minus x1 minus dot, dot, dot minus k minus 1 left, which actually is exactly xk, because we know that the sum of them needs to be equal to n. And we're going to choose xk of them. So this thing, even though I wrote it this way to be clear, is actually just xk choose xk. And when you have a certain number of things and you're asking what are the distinct number of ways to choose that number of things, well, that's just going to be equal to 1. So this is actually simpler than it looks. And again, the parallel term here, where you have p sub k to the power of xk. Super ugly, but you can actually do some simplification, and you can do this on your own sheet of paper. It's not too difficult. If you run into any issues, let me know. But you can simplify this whole mess to look much more elegant, just like this. So you have n factorial divided by x1 factorial, x2 factorial, all the way to times xk factorial. Times, this is a product notation, so this is saying multiply all of these terms, just like the sigma notation is saying add all of these terms. So p sub I to the power of x sub I. So you can see these terms are exactly taken from these terms here with no change. It's just all these bracket choose notation things that simplify nicely to become this first term out here. So that's just walking you through the PMF, the probability mass function for the multinomial distribution. And now that we have it, we can just plug in some real numbers. So again, let's say that we're sampling 6 people from FishCon. Let's say there is an underlying 50% probability someone would like salmon, a 30% probability they're going to like tuna, and a 20% probability they like cod. These things add up to 1, so that's good. And we're asking what's the probability 1 person of these 6 people likes salmon, 2 people like tuna, and 3 people like cod. 3 plus 2 plus 1 equals 6, so both of our conditions here check out, which is nice. And if we plug everything into this formula, we get 0.0216. Now, looking at this, you can start seeing already the uses of the multinomial distribution. this 0.0216 is a pretty low number, right? There's a pretty low probability that given a sample of 6 people from FishCon, from these global probabilities, that we would see something like this. And that makes sense, right? 50% of people like salmon. And so on average, we would expect 50% of our sample to like salmon. But here we're saying, wait, there's only one person that likes salmon? And in the same way, we would expect 20% of our sample on average to like cod. But here we're saying, wait, 3 out of 6, 50% like cod? That seems kind of unlikely, even given a small sample size like 6. So this probability is reflecting that, saying that if this was your true distribution, if these are the underlying parameters of your multinomial distribution, then it's actually really unlikely that I would see this breakdown in my sample of 6 people. And what that helps us do is make a conclusion about, well, maybe that means these are not the underlying parameters of my true multinomial distribution. So we can use this in the maximum likelihood sense to say that I got a sample in the real world. It looked like this. 1 person likes salmon, 2 people like tuna, 3 people like cod. I'm going to use this sample to make my best guess about what the underlying parameters of my multinomial distribution for the general population would be. And that gets us into the applications and also just recapping everything we learned today. So let's first recap everything that we have learned today. As I said in the beginning of this video, you can think of all 4 distributions we talked today as interacting as certain ones being special cases of the others. And so let's fill in a table to make that really, really, really clear. So we can do that in a 2x2 table because we just talked about 4 distributions today. On these columns, we have k equals 2 being the number of categories you have. So you have 2 categories or you have more than 2 categories. And you can think of the rows as being the number of samples you take from the population. So you either take 1 sample from the population or you take more than 1 sample from the population. Now, if you take 1 sample from the population and you have 2 categories, then you're exactly in the Bernoulli distribution. That's the first thing we talked about. The next thing we talked about was saying, well, what if you still have 2 categories, but you take many samples from that distribution, more than 1, and that gets you into the binomial distribution. And so now looking at this, we can see the Bernoulli distribution is just a special case of the binomial distribution where you set n equals 1. The next thing we talked about was saying, actually, what if you still sample 1 person, but now there's 3 categories, or 4 categories, or 5 categories. That gets you to the categorical distribution. And we saw that the Bernoulli distribution, again, for that reason, is a special case of the categorical distribution. In this case, just setting the number of categories equal to 2. And the final one, the main topic of the video, was the multinomial distribution, where we said we have sampling some arbitrary number of people from the population and having some arbitrary number of categories. And in that sense, you can think of the binomial distribution as a special case of the multinomial, where we're relaxing the assumption on the number of categories that we have. And the categorical distribution, by the same logic, can also be seen as a special case of the multinomial distribution, where we're relaxing the number of samples we take from the population. And of course, if you just kind of follow these arrows, the Bernoulli distribution also needs to be a special case of multinomial, where you're just restricting 2 things at the same time. So these are the interactions between the Bernoulli, binomial, categorical, and multinomial distributions. They're really all just the same distribution. They're all just the multinomial distribution, as you can see by all 3 arrows leading into multinomial. It's just that for certain events that come up really often in the real world, like flipping 1 coin, or picking 1 thing from several categories, it's more convenient to give each of them their own name instead of saying, here's a special case of the multinomial distribution. But this really helped me see that actually when you learn about these things, you're just learning about 1 thing. You're not learning about several things. So let's close out this video by talking about some applications of the multinomial distribution, some of which we'll talk about very soon in future videos. The first big application is LDA, which stands for latent Dirichlet allocation, which is a mouthful, but it basically is a way for us in natural language processing to assign topics to paragraphs or texts. Basically, look at a paragraph or a text, look at all the words in that paragraph, look at the topics that those words could be assigned to, and assign a topic to the piece of text overall. For example, if you work at a veterinary office and you treat dogs and cats, and someone sends you an email about something that's wrong with their dog or cat, you can run a LDA model automatically on those emails to classify that document as belonging to something about dogs or something about cats and assign them to appropriate members of your staff who may specialize in dogs versus cats. Another one is hypothesis testing. As we saw on the previous page here, if we calculate the probability of a multinomial distribution for certain observed samples, observed breakdowns of categories in the real world, we can look at how likely that actually would be if our underlying parameterization was correct. If we had a different underlying parameterization here, this probability would go up or go down, and that'll tell us relatively how much more likely would that underlying parameterization be versus the one we just looked at. So hypothesis testing is another big one in addition to topic modeling. And another big one is in Bayesian statistics. So in Bayesian statistics, something we talk about a lot are conjugate priors. And what we find out is that if the likelihood of something follows a multinomial distribution, so if we are in a case where we're picking 6 samples and looking at all the categories that they fall into, then in the context of Bayesian statistics, we should pick our prior and our posterior distribution to be what's called a Dirichlet distribution, the same D that's in LDA, which is not an accident, as we'll see in our LDA video. We should pick a Dirichlet distribution to be our prior and our posterior. So I don't expect that to be very enlightening right now because we haven't done any videos on Dirichlet distribution or LDA. But this video was a foundation, a building block, as we do go talk about those topics in the future. Mostly good to know that there are big applications of the multinomial distribution out there. And the other huge thing I would take away is this table here, where everything you've learned in the past about the Bernoulli and Binomial and maybe categorical distributions are really just leading up to those being special cases of the multinomial distribution. So thanks for sticking around. If you have any questions at all, please leave them in the comments section below. Like and subscribe for more videos just like this one, and I will see you all next time.